why do we care about JSON at all. Then some general architecture, which sneak peek is composed of 2 stages. So I'll talk about stage 1 and stage 2. Then some experiments to show that indeed they can do gigabytes per second, and then some conclusion and future work. So they quote 2 papers here. First, the Weld guy, who says that apparently big data applications can spend 80 to 90% of their time parsing JSON. I'm not really sure how true this is. But the point that I want to make, of course, is that there's more to query processing than just processing. You also have to ingest the data at some point, and if that is terribly slow, then you're going to slow down the whole process. A more reputable source from our own institute identified the acceleration of JSON parsing as a topic of interest for speeding up database processing.
Where did they do that? I forgot about that.
Yeah, I was also wondering if you did that, but it's a paper that you wrote with, I think, Guts as well, and I didn't actually read the paper, but that's the 2 names I saw.
Ouch! That was the wrong message.
Yeah.
Which paper? Which paper?
Number 2.
Oh, I don't have the. Are we together?
Yeah, sure.
I'll find it.
I mean, it's probably true. But did I say that?
Maybe you write papers sleepwalking.
You got a citation.
That's first author as well.
Yeah, the papers in the email.
Paper 2.
Paper 2. Database architecture for modern hardware, 2019. DuckStool seminar. It was not actually a paper, I guess, but
Oh, okay.
yeah,
I said it in the DuckStool seminar.
apparently you were quoted.
Yeah.
Or maybe someone
maybe
else
after
after
many
me.
beers.
I was thinking.
Somebody was recording.
Anyway, point is, unfortunately, there are still people using JSON, and if you have to analyze that data, you also have to ingest it, of course.
Yeah, actually, I met David Lemire at DuckStool.
Ah, really?
Private conversation. Okay.
Okay, so yeah, of course JSON parsers, they already exist, but the ones that are around don't really use any SIMD, and also a very branch heavy code. So typically you just, decode a stream of JSON character by character, and for each character you have to check, well, maybe I'm already parsing a string, so I have to check, well, is this character another quote, because then it would mean I end my string, or else is it something else. Basically you have to do a lot of branching for each character you decode, which means that CPUs cannot really look ahead, and so this can be very suboptimal. So they compare with rapid JSON and SESA JSON, which are supposed to be like the fastest publicly available parsers around. There's also something called Myson, which is a Microsoft JSON parser, which is kind of the inspiration for this one. That does use quite a bit of SIMD, but not as much as this work does. In a blog, they put it a bit more simply, and they just say, well, we were curious about how far we could do parsing with SIMD. So it's also just, I guess, the technical challenge. And so they say, parsing JSON is a bit more than complex than just finding nodes. It also implies some error checking. Of course, the very simple ones like syntactical errors. If an array starts with a bracket, it also has to end with one. It can only be ASCII outside of strings. Strings should be Unicode, which also implies some error checking. And applying SIMD for all of this is not trivial. And so the application of SIMD here is referred to as vectorization. So if I talk about vectorization, I don't actually mean batch processing, but the use of SIMD. So typically, like a JSON parser would just, like I said, decode the whole thing in one pass, character by character, just descending this whole tree of nodes. SIMD JSON does it a little bit differently. So SIMD JSON is the product of this paper, and is composed of 2 stages. The first stage is just one pass for all the data, just looking for the position of certain characters, such as colons, brackets, where an object starts quotes for strings, all of that. And then the second stage uses that information to actually parse whatever is in these nodes, so to parse the actual content. It also does some string normalization, parse numbers. And interestingly, the whole thing is signal threaded, which I think is a bit at odds with saying, I want to get the most out of the CPU, but then I just use one core. But that's what I went for. To be fair, it would be fairly easy to parallelize, I think, especially the first stage. So why 2 stages? Well, the idea is that stage 1, because all it has to do basically is find the location of of certain characters, that can be done without any branching. You can just keep a counter, and that can be done in SIMD. So this part is really fast. Now stage 2 is also a bit easier because now we already know the locations of all these, all these nodes. What they say in the paper is that you could, in principle, parse this and parse this and parse this all at the same time, but then later they actually don't do that at all. But they use that as the argument for why stage 2 should be faster because of stage 1. I don't know to what extent this is actually being done.
But what about escaped characters? Oh, there it is.
We'll
three.
we'll come. So stage 1. So basically, the main bulk of stage 1 is finding quoted substrings. Just from finding these structured characters or quotes, these brackets. Also, of course, we need to know when these structured characters are inside the string, because then they're not actually a syntactical element, but just part of the string. And then we also need to know when characters are escaped. So a quote in a string with a backslash doesn't actually end the string; it actually means a quote. So it is a bit more complicated, of course, than just keeping the counter. So this is basically the same story. So we just to be able to find a string, we don't really just care about quotes. We actually care about the unescaped quotes. And an unescaped quote is basically any quote that starts at an even position and has its first backslash preceding at also an even position, because that will mean you have an even number of backslashes, which means they don't actually escape that quote. And we'll use this in the following. So these are 64 characters of JSON, beautiful JSON, and you see this key value with very interesting stuff in there. So this is obviously a string, because this is unescaped, this is an escape, so this actually doesn't end the string, and this is an unescaped quote, so that will be one of the first strings. Now we need to find, given this data, where are the strings? First thing that they do is first they actually try to find all the backslashes. So you can just do a simple pass over these 64 characters. They do some SIMD stuff to keep a counter, and this is the result. So this is a 64-bit value. It's just a number. And it has two other values as well. One bitmap that denotes all even positions, and then one that denotes all odd positions. You actually kind of have to read this backwards, by the way. So this would be the start of the integer. So first, they need to find the start of all runs of backslashes, which is done by getting the original backslashes and then ending that with the negation of the backslashes shifted to the left, but it's actually to the right on the screen, because there's kind of a big ending then. And first, now we're only going to look at the even position, so ones that start at an even location. Then if you add this to this, what will happen is this becomes 0, you get a carry over here, this becomes 0, you get a carry over here, it becomes 0, and then finally you get a carry over here. So what happens is that adding this number to this will get you the end of all runs of backslashes starting at an even position. We also get this garbage in here, but we can filter that out. And so what we have now is the end of all backslashes starting at an even position. Because we now know the start and the end, we can actually count the difference we can check, if they both start at an even or position or an even and an odd position. If it's an even and an odd position, then we know that this is a quoted character. But they're actually both at an even position, so we find that whatever character is here is not escaped, and we can, of course, easily verify that that's true. There are 4 backslashes, so these are just 2 escaped backslashes, and that's something else.
But sorry, what is the whole talk about even and odd positions? Because any character can be at an even or at an odd position. It's
So
just one extra space, and what is even becomes an odd for all the rest.
So you have to do this twice. So you have to do this twice.
Yeah, you also do this for the
odd.
odd. Yeah.
You don't only even this, you have to do this test for even, and you have to do the same test again for odd.
Yeah.
Okay.
So this is at an even position. This is also an even position. Because of that, we know that there cannot be an odd number of backslashes preceding it. So you do the exact same for the other ones. Here we actually do get a result. So this one refers to this quote. This refers to that quote, and we can see indeed there's an odd number of backslashes preceding it. So we know that these 2 characters, whatever they are escaped. And this is then used in the following. So now again we have our input data, but this time we're looking for the quotes. Same manner as we found our backslashes. And then combining that with our previous results, so these are the escaped characters, we can now find all unescaped characters. Of course, this is not enough. We actually want to know where the strings are. Now we just know the borders of the strings, but we don't know, maybe this was a string and this is a string, but it's actually this part, of course. And through some bit magic, the carryless multiplication, they can actually do this. So what this does is, it's a prefix sum of, basically it's a prefix sum of this bit with the bit to the left, XOR with it. And once it hits in one, it will keep emitting another one until you actually get another bit set to one. So in this way you can basically mark the length of the ranges where the strings are at. Of course you don't actually have to iterate over all these bits. This is just a single instruction, so this is fairly fast, at least a lot faster than iterating over this whole thing. So now we found our quotes, our backslashes, but there are a lot more characters that I need to find. So also structural characters like this colon, comma, objects, all of that, and some white space characters that are of interest. They could do that in the same way. Of course, you could still have the same SIMD loop that just for each character counts where they are and then put it in some bitmap, but they deemed that would be too expensive. So instead they go for some table lookup. But of course, a very table lookup wouldn't be very SIMD, so they do something else. But first, this is what I kind of want to end up with. So you have these different code points. This is a comma. These are several structure characters, and it needs to be classified to some, to being something like 4 are the structure characters, 8 are the white space characters. This is of course something arbitrary. So what they do, they use some shuffle operation, which is basically some kind of table lookup, but only it doesn't use the full byte as an index into a table, but it only uses the 4 lower bits in a table, which means that you just have 60 values. Of course, we want to actually look at the full byte, so they do some magic here where they first look up the lower nibble in some table, then they look up the higher nibble by first shifting the whole thing by 4 in a different table, and then those two results are combined with an AND operation to get the final answer. So it looks something like this. To me, this is kind of black magic. So for instance, here you have, if you want to identify this code point to C, which is a comma, then the low nibble is C. This table gives you the value 1. In this table, the 2 gives you. So they extract an index out of these bitmaps. The way they do this is fairly simple. So say that you have one 64-bit word in your whole bitmap. You just continue to look at the trailing zeros, which gives you the position of the first bit in the integer. You add that to your index, and then you clear the first bit by this manner. And then, as long as there's still bits set in the 64-bit word, you continue try that again. This is actually compiled to a single instruction. This is also a single instruction, so this is fairly fast. The only problem with this is that because these there's only a low number of bits typically in these 64-bit words, this condition can be fairly hard to predict, which again can cause branch mispredictions, which slows the whole thing down. So they opt for more or less unrolling the whole thing by 8, which does mean that you will have excessive results written that are basically wrong, but they use a pop count before the whole thing to actually figure out how many iterations you actually need, and so at the end of the whole thing you can actually fix it. 8 is a heuristic that I found through experimentation. I'm not sure if that works in other data sets as well, but that's what they went with anyway. It does work apparently. This part is not that interesting.
I like their thinking. I like their thinking.
Yeah, I thought you would like it.
What if things span multiple blocks?
Well, there's still a while loop. So I mean, worst case, you just have to do it again. And in this case, probably because typically it will be less than 8. So in that case, you probably get a branch misprediction.
What this does is that this while condition becomes now very easy to predict, because it will be almost always false after the first. You will be done almost always. Okay, and once in a while there are more than 8, and then you have a branch misprediction, and you have to take the loop another time.
No, I mean like what if the string, like one block ends with 3 backslashes and the next block starts with 5 backslashes?
Good
Yes.
question. They don't mention that at all. Of course, that has to be some patching at some point, trying to connect those.
They will
those
have
things.
to feed the instructions always with some state.
Yeah, but they don't mention that.
Not
I was
that
actually,
sliding
I was wondering
window.
about this as well. I don't know. Yeah. Magic. So stage 2, so we got our indexes, and now we can actually parse the actual content. Stage 2 is a little bit disappointing because this is actually the same, kind of the same thing as any regular parser. You just have a state machine. You go through all these objects. You check where you are in the whole tree, yeah, you just parse character by character. Basically, this is mostly responsible for parsing the numbers and strings and stuff like that. So number parsing is again done in a regular character by character manner. There's one optimization that they make. So apparently, it's quite common to have at least 8 consecutive characters in, especially in floating point. So if that is true, which they can do this way, I'm not actually going to explain this because I didn't look into it, but if this is true, then basically you can do some kind of vectorized parsing, which is slightly faster than the regular one. But of course, that's just a minor thing. It's only works for those 8 characters, and I think it's more common that you will have less numbers than that in a row. Same thing for string validation normalization. So string normalization is about, you could have these kind of, this kind of web thing where you can denote a character by its Unicode hexadecimal value. So they have to be converted to their UDF-8 equivalents. So again, mostly on a character by character basis. The only SIMD thing that they do here is that apparently it's illegal in JSON to have a null character. So they go through all of the strings and check if there is a null character in there, which can be done with SIMD, but otherwise this is very character by character. So some experiments. They of course try their own stuff, but they also compare it with RapidJSON and SAJSON, which are like I mentioned before, the fastest publicly available JSON parser that they could find. And they try a bunch of different data sets. The idea is of course that depending on the content of your JSON, it may be faster or less fast to actually parse the whole thing, because maybe floats are easier or harder to parse than something else. Am I going to do the same thing? Oh wait, So the first thing they check is actually the number of instructions they're required to per byte to decode the whole thing. And the point here is that using their approach, they need quite a few less instructions than RapidJSON or SAJSON, so about twice as little. Of course, this is because of the whole SIMD thing. So the whole idea of doing SIMD, of course, is that you can do more work with the same amount of instructions, or in this case, less instructions for the same amount of work. Of course, you also hope that this translates into some runtime, and apparently it's also about a 2x speed up overall data sets. The actual absolute speed, of course, depends per data set, but they're always faster than their competitors. So conclusion is pretty basic. SIMD can speed up JSON parsing, and they say that the results suggest that maybe SIMD is underutilized at the moment in the popular JSON parsers. For future work, they talk about we still didn't do multi-threading. They said that stage 1 should be fairly straightforward to do because you have all these independent blocks, but like you mentioned, they're not completely independent, of course. So it's actually a little bit trickier than that. And also they don't really talk about the whole stage 2, but in their blog they do mention, stage 2 is actually kind of a mess. If you want to improve this, don't even look at stage 1, but actually see what you can do to parallelize that part, because that is still the bottleneck with all branching and character by character decoding.
And how is the performance kind of divided between stage 1 and stage 2?
I remember that it is 50-50 actually. But if you consider that really most of the work is done in stage 1, it's still very inefficient for that part, I guess. So that's it.
Where did you publish this?
It isn't published yet, but it will appear in FieldDB.
Really?
in particular stage 1, obviously.
Yeah, that's the
'Cause
part I
that's
like
what
as
they
well.
did. But yeah, as you just said, when you started at the beginning saying like, okay, it's single-threaded, but stage 1 would be easy to parallelize, I was wondering how.
Yeah, I'm thinking
for
the same
the
right
very
now.
reason that Ben and you actually pointed out yourself, and Peter mentioned, you know, you have the dependency. If you just go, even if it's a block within that block, yes, because in the SIMD, at the end of the day, to know whether or not a character is a quoted or not, you have to have the knowledge of the entire.
I mean, maybe
prefix of the file.
maybe you could basically divide the whole thing in the number of threads you have, and then at the end do some kind of patching thing. where
You
have
could
to-
do that, like, you know,
yeah.
maybe there's something possible that you do whatever you do with the bit magic per block and do
Mhm.
this, and then kind of once go through the results and swap bits,
Yeah,
figuratively
exactly, yeah.
speaking, depending on.
But that seems kind of expensive
on-
as well,
on
so I'm not
that
sure.
might certainly still linear and
No, I
and
don't
large
think that.
sequential.
I don't think that works. Even that algorithm,
Yeah.
because they squash bits that they think don't belong to strings,
Mhm.
Yeah.
but that needs to be flipped,
Yeah.
Yeah.
and so everything becomes different then because of that one.
But I think
backslash.
it's possible. I mean, it works, so we should look in the code. But I think just one carry bit that you for the slashes.
Well,
that have
you
to-
need a
Oh.
carry bit.
You need to
Yes.
propagate that.
Yeah,
Yes.
but of
But
course
that
it works
means that
when
you
they
cannot
didn't
do
parallelize it.
parallel.
Yeah, that's true.
Yeah.
Yeah.
But very often JSON parsing, is like you have some kind of dump that contains 10 million JSON documents. So the question is, maybe there is some way of finding the start of these documents, and then you have an independent anchor point.
Well, officially JSON is
Typic-
a single document.
No, but very often
but
it's-
of
it's
course
you
the-
have
yeah,
like
very often
collections.
they
They come out of a
them.
process
Yeah.
that emits a JSON every.
It's not
It's
uncommon
not
that
very
actually
JSON.
applications actually put the whole JSON on a single line and have a new line as the terminator of the record.
Yeah.
That's a pretty common standard to.
Yes.
Yeah,
If you don't want to search for the new line,
You
because
can-
that's another scan.
Yeah.
No, but you could do that in
You could
Simple,
do-
but
Yeah.
Yeah, but that's how they people.
But-
It's not uncommon.
yeah.
Couldn't stage 2 be trivially parallelized?
Yeah, that's what I'm
Because
thinking as well, actually. because
Then
there-
you have your whole structure,
Yeah.
and you just know here is a string, here's another literal. Just go and parse it,
Yeah.
and you know.
Like the first time I read it, like the first thing I thought is, okay, well, this is nice, we have the location, so now you can just basically in parallel start decoding that stuff. In that blog they mentioned stage 2 being terribly hard to parallelize. I didn't
No,
actually look into why.
No. There is one assumption in stage 2. They assume that they have to reconstruct the whole structure. This is not necessary. If I consider that actually as feeding into a columnary structure,
Mhm.
and you know that actually JSON actually is, has a schema, then you can perfectly parallelize and ignore that structure and immediately dump the results into n columns.
Yeah, but they're of course kind of agnostic about what it's gonna end on.
Yeah,
But that's
but-
maybe a
but-
limitation.
Yeah.
That's the limitation, and
Yeah.
probably in practice not relevant,
Yeah, that's true.
except if you're in a pure document environment.
Again, like if you would want to kind of put this into some kind of JSON representation, then speed is not your ultimate concern,
No.
because you're going to do whatever mallocs to create some tree, or I don't know. But this is very critical if you want to do bulk loading of JSON into columnar representation. Then the speed comes in very handy.
That makes sense.
Yeah, and this is one of the features that everybody wants to have. Snowflake was the first to have that you automatically recognize a JSON structure, and then you kind of put it into columns.
Yeah.
And then how does it work if you have one object that suddenly has something else?
Because somehow you have to kind of split it into a regular and irregular part.
Okay, yeah.
So, but very often people are the irregular part that they throw away because that's noise. That's kind of where you actually, so often you're glad that it's not there. Not always.
Any more questions? Thank you, Richard.